Okay, I'd also like to echo the thanks to the organizers for the opportunity to be here. It's especially nice to have a chance to spend a few days in a civilized country. So I'm going to be talking about the estimation of magnitudes of historical earthquakes, and the outline, of course, of my talk is in 3 parts. So we'll start with too big. And it's almost axiomatic that many, if not most, of the estimates of magnitudes of historical earthquakes were overestimated by earlier studies. As discussed in a body of literature by the late Nicholas Ambracies, shown here, Giving Bunny Ears to Roger Billum. And Nick focused on the pitfall of misinterpreting severe damage to very vulnerable structures that you have in some parts of the world. To summarize another body of work in a single panel, I've put together the plot on the left. And I should say that in this talk, I'm going to do something dangerous, which is namely summarize a fairly large body of work, which means I'm going to go over the details quite quickly. If you're interested in the details, I have a number of papers that I can point you to. But this figure on the left comes from the 2011 Mineral Virginia earthquake, which was one of the best reported earthquakes in terms of intensities through the Did You Feel It system. They collected over 140,000 responses. And I've looked for cities with, so US cities with over 20 individual zip codes for which intensities were determined. There turned out to be 20 of them. So I averaged the intensity residuals about the average for those cities, stack them, and not surprisingly, you find the distribution of intensities within cities is normally distributed. So what happened in conventional intensity studies is that the seismologist might have a fragmentary account saying that chimneys were damaged in Louisville, and based on that alone, assign intensity 7. If I have a pointer here. But the nature of archival reports is that they're going to focus on the more dramatic effects. So by definition, you're going to be assigning an intensity based on this part of the distribution, as opposed to the Did You Feel It system or REMI's EMSC, which assign intensities based on the representative damage. So when you look at classic intensities based on subjective interpretation versus the modern intensities that we're determining from a much larger set of data, you're really looking at 2 different things. So in a paper in 2013, I proposed a correction curve approach to correct from one type of data to the other. And as a test case, I looked at the pair of Parkfield earthquakes in 1966 and 2004. One of them you have the classic intensities assigned by hand. The other one you have Did You Feel It is shown here. And if you apply this approach, they magically collapse onto one another. Okay, so it's not surprising from a Bayesian point of view that many magnitudes were overestimated, because the one prior that we have in the problem is that we know that in any region, earthquake magnitudes are not normally distributed, are distributed according to the Gutenberg-Richter relationship, which means that many more earthquakes are small than large. So if you estimate a magnitude, typically with an uncertainty, it's much more likely that the true magnitude is below that estimate than above. So to focus on an infamous example, the 1811-1812 New Madrid earthquakes, which you've probably heard about, they loom large in any consideration of hazard in the central and eastern United States, as you can see from this big bullseye. The New Madrid seismic zone is illuminated by background seismicity, as shown here. So this is within this part of the United States. And I just wanted to stop, it's tangential to this talk, but I wanted to mention the question of whether or not these events are actually aftershocks. And I wanted to mention it in part because I've co-authored papers that say 2 different things, or give 2 different answers to that question. In 2004, in work with Roger Billum and Carl Mueller, we put together this summary figure showing that the distribution of microseismicity is quite consistent with the off-fault stress lobes from rupture onto major faults, which supported the idea that these are in fact aftershocks. But with Morgan Page, 10 years later, we tested rigorously the hypothesis that the sequence, the overall sequence, can be fit with essentially Omori decay, or okay, there's more to it than that, but we tested the hypothesis and rejected it. And so the way to reconcile these two results, that you have events that look like aftershocks but aren't aftershocks, I think is if these events, the modern events, are responding to creep on deep extensions of the fault that broke in 1811, 1812, with similar mechanisms and orientations. I think that would reconcile the two results. Okay, but getting back to this talk, our estimates of magnitudes for these events, so there were 4 principal earthquakes, hinges almost entirely from the felt reports that were interpreted initially in seminal work by Otto Nutley in 1973. His work produced these big balloon contours that have been reproduced many times over. In 2000, with colleagues, I revisited these accounts. I considered the biases associated with site response, considering the demographic patterns at the time, and estimated lower magnitudes than had been estimated previously. One of the criticisms of this work was that the intensities assigned were, quote, my opinion, which was never true because I had co-authors, but a few years later, with funding from the NRC, I parceled out all of the accounts of the earthquakes to 4 independent experts in historical seismology. I let them assign intensities, I averaged the results, and lo and behold, the intensities got even lower. So taking the intensities, averaging them, and analyzing them with the standard approach, the preferred magnitude estimates for the 4 events got lower still, closer to magnitude 7 than magnitude 8, and with a total sequence moment magnitude in the low magnitude 7 range. Some years ago, Calais and Stein put together this figure showing the deformation estimated across the New Madrid seismic zone from GPS measurements, and showing that as the data got better, the deformation rate was asymptotically approaching, if not 0, then a very low value. And so that inspired me to put together a similar plot of the magnitude estimates of the largest earthquakes, starting with Nutley's values that weren't actually that extreme, but then bouncing up to 8 3/4, and then also coming down in time. This is outdated. There have been a few later estimates that are arguing for higher magnitudes again. But in fact, if the earthquakes were magnitude 7-ish, they are not inconsistent with the strain rate estimates. Okay, so that was just one example. There's others. There's many others in the literature, many that other people besides me have looked at, but to show just 2 examples of earthquakes that I've looked at over the years, the 1892 Laguna Salada event is in some catalogs as a high magnitude 7 earthquake. Revisiting it, looking at the accounts more critically, lowered the magnitude to closer to magnitude 7. More controversially, the 1868 Hayward Fault earthquake, which is widely known or regarded to be a magnitude 7 or maybe 6.8. I recently looked at with Stacy Martin, and our preferred magnitude estimate is 6.5. So that's good news for Barbara, who lives along this fault. But again, so there's many examples. We're looking at back at earlier studies, taking into account the points that Nick Ambraci's talked about. The magnitudes dropped quite a bit. Sorry. But the second part of my talk is going to be asking the question of whether some historical earthquake magnitudes might in fact be too small. And this part of the work of the talk was inspired by plots like this, which you probably saw in the aftermath of this flurry of large earthquakes that we had, starting with the Sumatra event. People looked at this and noted the clustering and asked whether or not it was statistically significant. There were a couple of papers, nice papers published, showing that yes, there is clustering in this time series, but you can't demonstrate that it's statistically significant. Well, being a historian at heart, I was motivated to look back in the historic catalog to see what we could say about large earthquakes before the year 1900, and that produces this plot. So this is from 1700 onward. There's some dashed lines. This is separating the 8.5s and above from the smaller events, and then there's some dashed lines to show the centuries. I'm not going to talk in detail about the catalogs, but I can address that if you're interested. And so this puts together, this is a simple running average over 20 years of the number of 8.5 and aboves. And what you can see as the world became a more populated place in the 19th century, the number of earthquakes increased a little bit, and then in the 20th century, it increased quite a lot. So zooming in on this running average, you can see the dashed line is the average through the 18th century. It goes up a little bit, and then it goes up a lot. So basically, 1900, we invented seismometers, and earthquakes got bigger. And then in around 1950, we invented long period seismometers, and earthquakes got bigger again. So coming back to this figure and looking in detail at some of the numbers, one of the striking observations is that if you look at the largest earthquakes, 9.2 or above, the only ones in at least this catalog are in the in the latter half of the 20th century. To at least have some numbers to work with, I define great earthquakes as magnitude 8.5 and above, as shown here. So if you look at those numbers, the magnitude 9 and aboves, there were 3 in the catalog in the 19th century versus 5 from 1900 onward. And maybe not so different, but if you look at these 8.5s to 9s, there were only 3 in the catalog in the 19th century versus 17 since 1900. So if you look at moment release since 1700, you can see the rate since 1900, just drawing very simple lines, is calculated here. If you look at the 19th century using sort of a Hough catalog, which I've reviewed and updated some magnitudes, the value is half of what it was from the 20th century onward. If you look at the GEM catalog, which you may be familiar with, which resulted from a significant effort a few years ago, the problem is actually worse. It's the moment release rate through the 19th century is only a quarter that of what it is in since 1900. You can see the difference if you look at the magnitude distribution. Since 1900, you have this distribution of magnitudes compared to the 19th century. And I think it's inescapable that you're missing some of the largest earthquakes, or probably not missing them altogether, but underestimating their true magnitudes. So I was motivated at one point to try change point analysis, which is a simple approach to look at cumulative sums to identify breaks in a time series. I never published this, and I'll explain why. The initial results were sort of encouraging that, in fact, you see a break. So where the cumulative sums change slope, you interpret a change in the time series, and in fact, you see a break at 1900. You see another break at 1950. The problem is, there's something weird in my PowerPoint. It doesn't want to advance at this point. The problem is when you do the usual statistical test, randomize the catalog and repeat the same analysis as I've done here with just 7 different randomizations, you get results that look a lot like the real catalog. Just in this example of 7, there are a couple that look as where the results are not too different. So it's the usual result in seismology that the result isn't necessarily wrong, but you can't prove it, and sometimes I think you can't prove anything to the satisfaction of a statistical seismologist. But let's press forward to consider some specific missing grade earthquakes. And to start with, I've pulled out a few earthquakes that I consider missable in the sense that they're recent earthquakes that we know to be big, but if they had happened in historical times, I think it's very likely we would have underestimated the magnitudes from the information that we would have had. The Nias earthquake in 2005, known to be magnitude 8.7, did not generate a large tsunami or very strong damage. The 2012 Sumatra earthquake, which Pablo and others worked on, the oddball strike slip event, I don't think there's any chance we would have estimated a magnitude as large as 8.6, had that been a historic event. The Assam earthquake, which we just heard about, and the surface rupture wasn't identified until recently, and without the long period surface waves, would we have dared to go as high as 8.6? I don't know, but maybe not. And then to identify a couple of actual missing grade earthquakes, so again, missing in the sense that we know about them, but maybe we underestimated their magnitudes. The first is the 1843 Lesser Antilles earthquake. That the magnitude estimate for this earthquake has actually bounced around quite a bit over the years, as shown here. As I started to work with this, a very nice paper came out by Fouillet et al., also concluding that it in fact had a very large magnitude, focusing on largely on the near field accounts. Actually, a year after that, a study suggested the magnitude to be lower again. I stumbled across this earthquake by accident. I was looking for late aftershocks of the New Madrid earthquakes, and I found an earthquake that was felt over most of the east coast of the United States, from all the way up to New York and even into Canada and down to Florida. Quickly realized this was not a central eastern US earthquake at all, that it was this Lesser Antilles event. And I like this Google Earth representation, even though it's sort of, it's a crummy figure, but it illustrates that this earthquake was felt over about a quarter of the globe, also down to South America. So if you look at that intensity distribution, and you can quibble about the details, but if you look at the overall reach of that event, it's quite similar to that of the Tohoku earthquake. If you look at the intensities now versus distance, red is 1843, and again, you might quibble about these exact values, but compared to Tohoku in gray and Male in black, you can see that the distributions are quite similar. So I hesitated to come up with a precise magnitude estimate for this event, because the calibrations that we have for this kind of analysis really aren't any good when you get to magnitudes this high. They just aren't constrained, but I think the data support a magnitude at least as high as 8.5. Another candidate missing grade earthquake was an 1841 event in Kamchatka. It's in the catalog as a low magnitude 8. Abe looked at this among other events, and he concluded that it had a high tsunami magnitude of 9 based on the tsunami observed in Hilo. Okay, so with the time I have left, I wanted to sort of address the question of trying to find magnitude estimates that are just right. And let me start with this plot. So this is something that I really only started to appreciate in the last few years in the context of some work I was doing on induced earthquakes. What this shows is the simplest possible one-corner velocity source model So it's a one corner omega squared decay. It's ignoring all of the complexities of breakdown and scaling that we heard about, or that Barbara was talking about decades ago. But the result that it shows is something that people like Tom Hanks and Dave Bohr were talking about back in the 80s. If you look at how the high frequencies scale with moment magnitude from 7.6 to 8 to 8.4, the high frequencies scale only weakly with moment magnitude. Whereas stress drop, if you fix the magnitude but vary the stress drop over 2 orders of magnitude, so 1 megapascal, 10.1, the high frequency radiation actually varies quite strongly with stress drop, such that a 10 megapascal magnitude 7.6 generates essentially the same high frequency shaking as a 0.1 megapascal magnitude 8.4. This is a problem for historic earthquake studies because if you only have intensities to constrain magnitude, intensities are basically telling you about energy release between about 2 hertz and 8 hertz, that's overwhelmingly what's important for people and structures. So you've got information over this frequency band, and you're trying to determine what's going on down here. It's basically not a winning game. And so what I realize somewhat belatedly is this is really the granddaddy of uncertainties in trying to estimate magnitude from intensities. So coming up with magnitude estimates that are just right is going to be a tall order if we're constraining them primarily from intensities. Where you have tsunami observations, I think that's an important constraint. Obviously that, we should be looked at and factored in. There's a list of events looked at by Abe for which he inferred high tsunami magnitudes. And there's some early events in here that I think might be worth looking back at. But I wanted to conclude with the 8 minutes I have left to present some recent work asking the question, what magnitude estimates are just right in California? And here I'm getting away from great earthquakes a little bit. I'm going to be talking about some more moderate and moderately large events. So there's a old observation that has been vexing for researchers trying to quantify seismic hazard in California that's summarized by this plot. And this picture is to remind me that I'm doing this work with Morgan Page, shown here with a T-Rex. But the basic observation, which has been recognized for a long time, is if you look at the instrumental catalog of earthquakes in California, you get a nice B-value distribution, maybe tapered at the high magnitudes, versus the historic catalog, you see the incompleteness, but then above magnitude 6-ish, it's quite a bit higher than the instrumental record, which has led to suggestions that California has been in an earthquake drought since 1906. And in fact, if you look at the United States as a whole, if you look at the list of the top 10 earthquakes in the contiguous United States, using what I think are the authoritative catalogs at this point for the 2 regions, you get this list shown here. So again, these are the top 10. And just to help draw your eye, there's only 2 of these events that happened after 1906. All the rest were 1906 or earlier. Oh, and Landers falls off this list because it's in the catalogs as 7.28, I think. Okay, so let's look at California. So this is the USERF region. USERF is the Uniform California Earthquake Rupture Forecast project, which has been a big consortium effort to produce an earthquake rupture forecast for California. There's been a lot of work done looking at this part of the world, so that the USERF region includes California with a margin of about 100 kilometers in every direction. Okay, so if you look at moment release in California, in that extended region since 1800, this is the result that you get. And you can see things increasing more or less linearly, and then you can see this earthquake drought. If you just do the simplest possible calculation, we're missing a moment equivalent to about 1 magnitude 8 or 2 high magnitude 7s. So with any cumulative moment release curve, it's going to be dominated by the few smallest events. So I looked at the moment release associated with only the 6 to 7 events in California starting at 1850, at which point the catalog should be fairly complete for those magnitudes. You can see that the moment release is fairly linear up to around 1930, and then it flattens. So in this case, 1932, of course, is when the instrumental catalog begins. So seismometers were installed in California, and in this case, the earthquakes got smaller, which is or the rate fell, but this rate fell by a factor of 2, which is equivalent to the same rate with the earthquakes being 0.2 units smaller systematically. So I'm going to skip over the details in the interest of time, but if you do play the same game with the central and eastern United States, take the biggest earthquakes off the table, look at the moderate earthquakes, you see the same thing. You see a fairly linear increase up to around 1930, 1940, and then things flatten by a factor of 2 to 3. You see the induced earthquakes kicking things up again in recent years. So in fact, you can play the following game. Let's subtract 0.2 units from all of the pre-instrumental earthquakes in California, so the big ones as well as the moderate ones. And then this curve with the break in it turns into the gray curve, which is magically linear from 1800 onward. So from this, one might conclude that all of the pre-instrumental earthquakes, including the larger ones, 1906, 1872, 1857, were systematically overestimated by 0.2 magnitude units. Now, there's about 6 different ways you could criticize that. We've heard some intriguing evidence that, in fact, that fault systems may have clusters of large earthquakes separated by relative dormancy, so there may in fact be an earthquake drought. I haven't looked at any of these events individually to revisit the magnitudes. So maybe the conclusion isn't hard and fast that there has been this systematic overestimation. But yes, no. I'm essentially done. This is the last slide. You still have to explain this, that when regional monitoring started a little bit later in the central US than in California, the apparent rate of moderate earthquakes dropped significantly. So I seem to be perfectly timed. The conclusion, the first one isn't new, that many, if not most, historic earthquake magnitudes were overestimated by earlier studies. In our quest to revisit the magnitudes, I think we're left with a largely irreducible uncertainty associated with stress drop variability, which for historical earthquakes is generally going to be unknown and unknowable. But you can't have your cake and eat it too. So what do I mean by that? At least with the New Madrid earthquakes, at one point some researchers were arguing for very high magnitudes, which was problematic because there was evidence that the faults involved were not all that long. And so the answer was, well, they were high stress drop events. But you can't have high magnitudes and high stress drop, because if you tried to close that loop, you would over-predict the intensities that you have. If you're constraining magnitude from intensity, you can have high magnitude and low stress drop, or low magnitude and high stress drop, but not both. That said, I think it's inescapable that some great historic earthquake magnitudes have been underestimated. The earthquakes are probably in the catalog, but are bigger than we think. The consideration of rates in an area, as I've done for California and the central eastern US, may give an estimate of the systematic biases with the estimation of historical magnitudes. And maybe there is, in fact, no significant earthquake drought in California. In the central US, there is an apparent earthquake drought. We haven't seen a New Madrid or a Charleston earthquake, certainly, since 1929. With the simplest interpretation, well, maybe I don't want to try to summarize that in the negative time that I have. So instead, I thank you for your attention.